Hi, everyone. This is Tom Salemi, Medical Design and Outsourcing. Welcome to a super great webinar we have for you called Designing Medical Devices for Additive Manufacturing, sponsored by HP. I had the privilege of hosting these folks on one of our Device Talks Tuesdays a couple of weeks ago, and I promise you it'll be a great presentation. Before we get into it, I'd like to remind you that this presentation will be available on demand. So when, not if, but when you conclude this webinar and realize a colleague or friend really would benefit from it, make sure you let them know that they can watch it on demand, they can register, they can ask questions. It's almost like being here live. We'll make sure we get the questions to the folks on the panel. You can collect the slides, of course. They're available in the resource widget. We will have a Q&A session. It'll be towards the end of the webinar. I'll help facilitate with those questions. And if you are tweeting, thank you very much. Please use hashtag MDOwebinar when you do, so folks can see all of the posts. Now, that's enough from me. I'd like to hand over this presentation to David Johnson, Application Engineer at HP. Take it away, David.
Thank you so much, Tom, and thank you everyone for attending today. My name is David Johnson. I'm an application engineer for HP, focusing on their 3D printing line, which is called Multi-Jet Fusion. I cover the Midwest based out of Chicago, but I'm also helping build our medical equipment segment, which is what brings me here today. Drew, if you want to introduce yourself.
Yeah, my name is Drew Boggin. I'm the Sales and Marketing Manager for Avid Product Development. We're a 3D printing parts provider located in Loveland, Colorado, just north of Denver. And we have been a longtime user of the HP Multi-Jet Fusion platform.
Hi, everyone. My name is Pete Temple. I'm the Operations Manager here at EI Medical Imaging. As a company, we design and manufacture diagnostic ultrasound devices specific for the veterinary industry. Personally, I have a background in electronics, but I've been here at EI Medical for 20 years and involved in every aspect of the product lifecycle, design, and supply chain. We're also located here in Loveland, right near Drew with Avid, so we've worked together on some parts, and just excited to share what we've done.
All right, so today's topic, we'll be going over design for additive manufacturing, which is also shortened to be called DFAM. Those of you who are newer to this industry, additive manufacturing is, I'd say, the industrial way of saying 3D printing. So just when we say AM, additive manufacturing, that's typically what we mean. What we'll be going over today is looking at different design strategies and the benefits of approaching that with 3D printing. For Multi-Jet Fusion, we'll be going over some general design guidelines and the actual value of designing for that process. We're going to go half presentation. The other half, I will be letting Drew and Pete talk their actual customer use cases of kind of utilizing this entire process. And we'll have questions available as we go through. So if you have anything, feel free to ask in the chat and we can go over that. So the thing I always like to start with is making sure it's understood that even in the additive manufacturing area, there's a lot of different type of technologies. I'm sure a lot of people are familiar with the material extrusion, which is a thermoplastic filament. That's probably one of the most easily accessible and widely used formats. So with Multi-Jet Fusion, we are what's considered a powder bed technologies, and each of these technologies have advantages and disadvantages with how they actually make the part. They all are similar that they are printing apart layer by layer, but how they actually create that layer is kind of where these are segmented. So the benefits with this is the product capabilities of the actual printing process. So with Multi-Jet Fusion, you don't need to have support material. We also have isotropic properties material on the material side. And because of the recyclability aspect of the process, we do have very competitive material pricing and also material selections. So going into how Multi-Jet Fusion actually works, As I mentioned, it is a powder-based process. So we start with a single layer of thermoplastic powder that's spread across the entire build platform. We have two types of agents. So we have a fusing agent, which will be laid down in the geometry of the part. And then we have a detailing agent that kind of goes around that fusing agent. And what those two agents do is the fusing agent is going to absorb heat. Think about like a black car on a hot day. It's going to be a lot hotter. So that same concept is that fusing agent is absorbing the heat in the system, whereas the detailing agent is giving it a like clean, crisp cutoff so that the heat isn't kind of absorbed outside of that location. And then with that, we have a fully fused material. With how the heat is applied, that is the way that we're able to get isotropic material properties. With 3D printing, typically it's anisotropic, so you have your X and Y material property, but your layer to layer, which is the Z dimension, typically is weaker because that layered adhesion isn't as strong. With this process, you don't really have to worry about that, and that makes things a lot easier when you're kind of thinking about design and process. So I'm going to go into a quick video just that will give you a wider visualization of what this actually looks like.
The printing is a thermal control process that begins by applying a layer of powder material in the printable area. In the opposite direction, in one continuous pass, the print carriage selectively applies fusing and detailing agent using fusing lamps to raise the energy and fuse the current layer with the previous layer only where the fusing agent was applied. During the whole printing process, the heating lamps and thermal camera placed on the top cover are used to control the temperature on each layer, ensuring its consistency across the printing job.
Hey, David, we're not hearing you.
Yeah, sorry, I caught myself.
There you go.
Presentation issues. So hopefully they give you a good visualization of the process. So that's happening layer by layer as it goes through a full print job. And when we think about designing for additive, there's typically an evolution that we see with a lot of our customers. They'll typically take a previously designed part, whether it's from CNC, injection molding, other type of conventional manufacturing, and they'll make it into a model that can 3D print. But there's usually several steps going into the direction where we want it to go. So kind of go into an initial printable design, they'll go into lightweighting design, and then go into, say, the final evolution of the absolute perfect part for the process. And I like to show this because when you take a look at a part, you have to really unlearn everything you've been taught with that design. And you really have to go back to, what is this part trying to do? What's the purpose? What's its function? What are the forces? And taking that step back allows you to see how differently you can actually approach this part. And that's the thing with 3D printing, is it really gives a final design freedom and kind of taking what you think you can actually make in your head and make it a reality. So even though there's a lot of design freedom, there still are processes to understand and make sure is aware when you going through this process. There's still limitations. It's not completely open to whatever you want to print, but the limitations are minimal compared to some of the other manufacturing processes that exist. And whether you know it or not, you can see some of these limitations in designs, like, for example, of injection molding, which has been around since the 1800s, still utilized today. But when I see a part that has a uniform wall thickness, draft angles, I typically know that this is a part designed for injection molding. So it takes some time to kind of backtrack to figure out how do we actually make this part work for 3D printing if that's a goal of actually making this end-use part. So here's an example of some of the design evolution looking from a injection molding design to a multi-jet fusion design. As you can see, there's a pretty significant reduction in surface area of the part, but there are some unique things that do happen as you design for additive, where injection molding, you would be concerned about the die draw. When you go to 3D printing, you have to be aware of the build direction and orientation. So even when you have, say, a perfectly designed part for additive, another variable that didn't really exist is how you actually print that as far as the part orientation. So with our process, you can print it for accuracy, where you want to get the most critical dimensions in the X and Y plane to get a really tight tolerance. You can print it for surface finish and strength. There's certain orientations that give the best visual look for the part, or you can be optimized for cost. And this will make the part cheaper, allow you to get a more efficient packing density or the total amount of parts that take up an entire build. So these are all things to really consider as you're evaluating how to actually print this part. And another thing they can be considering is something where injection molding, you're considering wall thickness as and draft angles. You want to make sure the part comes out, it doesn't get messed up with the tool design. So on the 3D printing side, you want to avoid sudden changes in printed surface area. I always say this entire process is a giant battle of thermodynamics. So if you have this part in the top left, and you go from really thin walls around the edges to a completely flat plane, if you think from a heat perspective, this is a pretty big difference between temperature going from layer to layer. So you might see some problems when it comes to the part quality of the end-use part. So you want to take in considerations of how do you control that layer-to-layer printing with heat, where you can actually create the design in different ways where it's still functional at the end part, but this is a better fit for the actually printing process as opposed to the actual design of the end-use part. So these are some of the things that are different and kind of take a new perspective as you're looking to design for 3D printed parts as an end-use product. So one other thing which I do want to mention, not dig into too much, is thinking about packing density when it comes to a build. So with our process, we have a certain percentage of packing density. So how much volume do all the parts in a single build take up? And there's preferences of ranges that we like to hit. You can go higher to get more economics or a more economic build, but you're balancing part quality and costs similar to that orientation. But also how you design the build can also play a pretty big impact about how your parts come out. And before moving on, Drew, do you have any additional things to add with that?
I think that one thing from our point of view and working with customers like Pete is communicating with your parts provider if you're not the ones printing, or with your build planner on what critical surfaces are, so that that person building the parts can best choose how to orient the part, whether that's for cosmetic or mechanical or cost effectiveness.
All right, great point. So now that we've kind of gone over some of the high level thinking when you look at a final 3D printed part, we're going to go into some general design guidelines. And these are design guidelines specifically for multi-jet fusion. As I said, each of those segment technologies all have their own ways of designing for the part. So one of the things we typically get are pretty large parts that someone wants a 3D print. You either can't print it as a whole part, or it's just very expensive because of how much space that part takes up. So there are different ways to look at how to essentially create an assembly for a final part. We have fittings in the design, threaded unions where you'll heat sink a part, put in a threaded insert, and you have it then a essentially mechanical assembly process. You can design a snap fit into the final part. So you have parts that essentially snap together and hold in place. And for more, say, forceful applications, you can actually do adhesive bonding. So it's almost like creating a 3D puzzle piece with different types of connections that you can use with adhesive, or you can do something like ultrasonic welding where you're actually melting the material to bond to itself. So these are a few different options when you're looking at doing a more complicated part. And here's an example of a bumper that is printed with multi-jet fusion, utilizing the ultrasonic welding. And you can see that on the left, we have the original parts. They've gone through some post-processing with painting and priming to get a really nice finish. So these are the things that are possible with this process. So thinking about the design, there's different ways to optimize that design when you do have a close enough part design in mind. When it comes to the process, we typically don't want wall thicknesses below 2 millimeters. It gets a little bit hard with the balance of the thermodynamics of the process to really get a consistent part that has the material strength, but also the part surface quality. As you get smaller, you kind of battle with that balance. And you do have the option to hollow parts because we don't want a giant block of material, as we talked before with the thermodynamics layer to layer. So if you do have a more blockier part, you can hollow it with a few different softwares offer that option. And you can also look at what's called latticing. So instead of having a giant block of material, you're using a lattice structure, which still provides a lot of material strength, but greatly reduces the overall material usage there. The other thing you can look into is what's called topology optimization. And if you understand the forces of the part, you can utilize the material in the best distribution to kind of support those forces and get some very unique designs. When you take this approach, there's typically two different ways of looking at it. If you have a part that exists, you can redesign it with topology, which is kind of the part on the right there with the hook, or you can do what's called generative design, where you don't have a part model in mind yet, but you can create, say, criteria of dimensions, connection points, forces, and you'll actually get iterative designs of a final part that you can use and then 3D print. And here are a few examples of what that looks like. As I mentioned before, it's a very unique look. It's very organic, which when you're coming from conventional manufacturing, this is kind of a shock that these are parts. But one of the advantages with MGF not having that support structure requirement is the complexity of these parts. If you were to print these in other processes with support, these would be an absolute nightmare to remove. Your technicians would not be happy with you if this was a design that you're trying to run through the 3D printer. But it allows you to reduce print time. Often you can reduce the total cost because you're using less material, less fusing agents. And for a lot of applications, it also allows you to lightweight the material. So the final either assembly or part itself critically loses a lot of weight when you kind of take this approach. So with our process, there are a ton of different design iterations, concepts for accuracy, aesthetics, and I only had a very small amount of time to go through some of them at a high level. We do have what we call the MJF handbook, which digs pretty deep into a lot of these subjects. I have a URL here. If you're interested, you can download it and kind of take a view of different things to really consider, especially if you're looking at this as a final approach to your product. So moving to the part where kind of showing that we do this entire process for our own parts. So in HP's 3D printers, we do have 140 plus parts that we actually print with our own printers. So we've redesigned them, taking a look of how to really optimize them. So I do have a few examples of what this looks like with parts that we have in our own printer. So looking at the initial design or traditional assembly, we have multiple parts, a lot of assemblies, fasteners, and different types of parts. When we take this design approach, we can unify it and simplify it into multiple parts till one or two assemblies. And then when we look at how to actually print this from the final design, making a foldable fixture actually allows a increased production for this part. So we can get more parts fit into the final process and allowing that to be a bit more cost effective for the parts that we are producing internally. So this part is on the receiving end in our fusing agents, which is on the right side of the machine. And this video will kind of give you a quick example.
Yeah. Hi, Ian. Okay.
So that's the part in process as it's being used. And the second example I have is what HP calls the mighty duct. So this was a really good example of designing for a process, but also utilizing the design freedoms of multi-jet fusion to even improve the overall performance of the part. So we took the initial concept, which was an injection molded design, into multiple parts. We simplified the overall design into a single part, which saved cost reduction, assembly time, and then taking that unified part, we put it through a computational fluid dynamics to see what type of design got the best type of air movement through this. And that resulted into what you see in the right. So with this process, we saved about 35% in cost reduction, but we also improved the flow of this air valve or air intake manifold by about 22%. So this is where the value really exists with additive manufacturing and designing for it. You know, there's companies that will take this injection mold design and just 3D print that, which you can do, and it might be a little bit better. However, when you really take a step back, design for this process, say, you know, what can we do now that we didn't have options before? That's where you really get the value in this process and the end use part overall. All right, going into one of our customer use cases. We have a few more before we start talking with Drew and Pete and digging into their actual parts that they're utilizing as well. So this is a blood sampling device by Averix Engineering. And this really shows the advantages of simplifying your entire part from a multiple assembly to a single or double or a two-part system. And they really took a few different aspects of what was made before in either sheet metal or injection molding and found a way to 3D print it, made their process a lot more efficient. They also saw cost reduction, lead time reduction. So overall, this was a very successful implementation of taking a design for additive approach. My favorite part of this case is this section right here. So this was all sheet metal, a lot of fasteners. I believe it was the 26 parts. And after they took the design approach from that process to 3D printing, they simplified it into two separate parts. So you have all the sheet metal got replaced by a single MJF part. And then on the top side, they had another MJF part, but it was still a little bit light. They need a little bit of weight there to actually hold all the samples down. So they did another post-processing where they plated it just to give it a little more weight than the bottom part. And after they went through that process, it worked perfectly. And really was successful with their implementation of how to make this work for multi-jet fusion. So this, I know, is not on the medical device side. However, how this design was done, I think will definitely translate into some of your applications and what you're working on. It's utilizing a lot of the design concepts I talked about before, but when you have total units, which might involve pneumatic systems, electrical systems, fluid systems, it gets a little complicated putting that all together. What I love about this part is they actually utilize the design of a 3D printed part to take over some of those fluid and pneumatic systems. So I like to show that just because this is kind of the next level of designing for additive as you're going through the process, where you can actually see and integrate some of these systems that are outside the 3D printer into the actual final part. So I think that's a wonderful place to end, as that case kind of brought everything together that we talked about today. And I'm going to hand this over to Drew and Pete, so you will not hear my voice for a bit. Drew, you know, I'll have you introduce yourself, your company, and Pete as well. And also important just to explain the relationship between your two companies and kind of how that started. And then we'll go into some of the parts that Pete's company, EI Medical Imaging, actually created with this process, and we'll leave it from there. So I will let you take it from here.
Thanks, David. My name is Drew Boggin, and as I said earlier, the sales and marketing manager here at Avid Product Development. Avid Product Development was founded about 10 years ago and started as a contract mechanical engineering design house, and slowly we started acquiring 3D printing technologies and printing parts for our customers. And then when HP developed the multi-jet fusion platform, we jumped right in and pre-ordered one right when they announced. And since then, the 3D printing part of our business has really taken off. And we still have that backbone of engineering for our company and helping our customers iterate their designs to best utilize the technology. We're about 27 employees today, and we have ISO 9001 certification. So we don't have the medical certification, but we do have the 9001. And I'll let our customer, Pete, introduce himself and his company.
Hi, everyone. It's Pete Temple again, the operations manager here at EI Medical Imaging. And here at EI Medical, we manufacture and design diagnostic ultrasound devices specific for the veterinary industry. So these devices are used for all the same applications that you would on the human side. If you were pregnant and you wanted to go and check on the baby, just internal medicine, all sorts of things, just to diagnose everything you would need to. And being that we're veterinary specific, we cater often to very large animals, livestock reproduction, zoos, things like that. So we've developed a wide range of products that are kind of specialized for that. We met with Drew a couple of years back when we had a need to just rapid prototype an enclosure for a new design. Once we kind of learned a little bit about each other and a little bit about some of the capabilities at Avid, we discovered we had a couple of products that were worth looking at using some of the new technology for 3D printing directly. And that's kind of how the relationship started. As a company, we're about the same size. We have 25 employees. We've been around for about 35 years now. Personally, I've been with the company now for 20 years, so it's kind of my lifelong career to this point. But yeah, it's been fun to explore these alternative ways of doing things. It's kind of opened our eyes a little bit to finding a balance between cost and lead time and just design freedoms. So that's just a quick intro about me.
All right. Thank you, Pete. So Drew, when you get a customer like Pete coming in, how do you navigate what they're looking for? Because I imagine a lot of them are like him coming in looking at prototyping for parts that might go to an injection mold or something like that, and educating them to make them understand like there are a lot more options looking at additive from an end use part and production side.
Yeah, I think a huge part of this industry is still educating our customers and educating everyone downstream. So I think having those meetings, whether it's a Zoom call or a face-to-face meeting like Pete and I were lucky enough to have, and showing them some actual parts. So getting, their part in their hand printed in MJF to understand the quality that this technology is capable of achieving. And then ultimately understanding that the price point, that how cost effective this technology is, and that it is competitive at the right quantity.
Yeah, and then I know you have a few other additive technologies at the company as well, and also actual product development from a design side. How do you typically choose, which technology makes the most sense for the customer, and also if, offering some of your services to actually help design for a better 3D printed part if they're looking at that as like a production option?
Mm-hmm. Yeah, so ultimately it's going to come down to what the part requires. So whether it's a material that's driving the choice in what technology, or the surface finish, or things like that, there's a lot of things you can do after the parts are printed. So if it needs to be smooth, we have equipment that can chemically smooth HP's parts, and ultimately there's a lot of factors that go into which technology we're going to choose. Ultimately, if the product is looking at HP longer term, we'd like to prototype it with HP so that we can start that design iteration right away and keep that moving.
All right, thank you. If it's all right with both of you, I think I'll move on to the first case with EI Medical Imaging.
So this is a head-mounted display that we've designed. So our ultrasound devices, because they often, we have to go to the animal, we can't always bring these large animals to us. We have a head-mounted display that allows the user to kind of strap the machine to their body, put the head-mounted display on, and it gives them kind of mobility and viewing freedom when they're outside in sunlight. It lets them kind of work around the animals without kind of being tethered to something that's on a table. And so this has been an important product for us. And what happened here is this product was designed for injection molding. It was injection molded for a couple of years, and then in the more recent device or electronic component shortage, we ran into an issue with our vendor that supplies one of the circuit boards inside of this head-mounted display, and they had to make a very significant design change to the electronics inside of it, and that caused that circuit board to grow quite a bit. And so we were left with a pretty big dilemma, because we had a circuit board that was growing so much that it wouldn't fit into the existing enclosure that was injection molded. We had current orders coming through the pipeline and a current customer base that was relying on this product. So we that's where we reached out to Drew at Avid and worked with our mechanical engineering team to first redesign the part just to fit the new electronics. And then we started exploring, well, can we 3D print the part for production, or even in the interim to get through a delay in manufacturing parts. The change had happened so significantly that we would have had to kind of scrap the old injection molding tool and start over, and there was a lead time associated with that just wouldn't work for us. So we reached out to Drew and our mechanical engineering team and kind of redesigned the part, and we've kind of discovered that using this technology, we've been able to directly 3D print these enclosures, and to date we've manufactured about 150 of these head-mounted displays using 3D printed parts, and they've worked well in the field, and then we've been kind of happy to continue on and not have a delay in our production.
So Pete, can you dig into, you mentioned the timeline with going through retooling. Can you go through what that process would have looked like with retooling costs, the timeline till you could actually produce parts, as opposed to the path you did go down? Yeah. So absolutely. So either path required the redesigns. So that took a couple of weeks, but once that was done and we passed it to the injection molder for quote, they had determined that the tool couldn't be modified for the new design, so it had to be started over. And they had quoted an 8 to 12 week lead time. We were running pretty lean on inventory, so we had about a 4-week lead or supply of components in our inventory of the old PCB. So we had to make we had an overlap there that was going to be a real problem for us. The other thing was that tool was quoted at about a $30,000 cost. We went back and we looked at, well, how many of these things have we built? We're a relatively low volume manufacturer, and in the life of the product to date, we've made about 500 pieces, and we kind of, it's a simple math formula, but the ROI was somewhere in that 500 to 600 parts for the tool when you compared it to the cost of 3D printing. So we weren't sure if the design is going to continue to evolve and change, especially given the volatility in the electronic component market. So it really made a lot of sense to try using 3D printed parts and then see how that could really benefit us and then keep us running in a short term and save some cost. Yeah, and the question for both Pete and Drew. So when you made that decision that you were going to take the multi-jet fusion approach with actually producing these parts, what opened up as far as the design freedom that went into that next iteration of this new part design?
Yeah, we're still exploring that a little bit. I think that the first example we've used is inside of this head-mounted display. There's a feature that holds the display in position. And previously, when it was injection molded, that feature we had a third component that kind of had to screw on top of it and hold it down. But because we can use the 3D printing technology and we're not limited by some of the constraints of injection molding, we were able to design some snaps, and now the displays just snap in. That's made it a quicker assembly. It's reduced the number of parts. So it's still a little bit in the infancy of exploring how far we can go with that design and what we can do with it. So we really just had a quick get from injection molding to something that we can print right away, and so we're evolving as we go on.
All right. And Drew, any comment to that with kind of the redesign process that you've been working on with Pete?
Yeah, I think, Pete's team did the design legwork on this example. I think the other one we're going to dive into next had a little bit more of your typical DFAM principles. But one thing we did have to communicate back and forth on with this project was, there is a tight tolerance component to this part that needs to be pretty accurate. So we had to communicate back and forth, Pete and I, to adjust the print orientation so that it worked best with the other components that need to fit inside of it.
All right, thank you. So I think with that, we can, just to keep on pace with time, move on to the second product from EI Medical Imaging. Pete, you want to kind of give a background of what this part is and the process that you've currently gone through?
Yeah, absolutely. So it's kind of a scary looking device, but what it is basically an arm replacement. So it holds the transducer. In large animals, to get to the reproductive tract, we have to enter the animal rectally and use the ultrasound probe there. In years past, the practitioner would just hold the transducer in their hand and they would go in with their arm. And what we've learned over the years is that can cause a lot of fatigue. Often these are high volume applications where they might scan several hundred animals in an afternoon, and it can cause a lot of fatigue. And over the years, it caused a lot of just kind of physical wear and tear on these practitioners. So this device was developed as a probe holder so that the practitioner could use this in place of their arm. An important consideration here is that in the center section, it's a flexible device. So it's got kind of a malleable center section with a metal bar inside of it. And this allows the practitioner to set the angle of the device. So as large animals, as their gestation kind of goes to term, the baby will kind of drop over a pelvic brim, and they'll have to change the angle of this device. So that allows the practitioner to kind of adjust it and make it work for their needs. Initially, this device was made using a cast urethane process. So what we would do is start by 3D printing a kind of a sample part. That sample part would be used to make a mold, a silicone mold. That silicone mold was then used to cast urethane to make these parts, and it was done in a few different stages. So with the two ends were a hard material, and so you'd start there, you would cast those, and you would embed a metal rod in it, and then that would have to cure, and then you would cast the center section with the more malleable material. And a couple of constraints there were that one time, that process, you could only make about one part per day. And then another was that these silicone molds they had kind of a short lifespan, so you could get about 25 parts out of them, and then they would have to be remade, recast. So the overall process was very labor intensive. It never made sense to injection mold this part because it's a relatively large part. We support several different transducers, so we had different ends that had to be fit in there. So we worked with this process for several years, and it was expensive and it was slow. And after a few years, we started developing we'd actually, for lack of better terms, that center section had some sort of chemical reaction with some of the cleaners that people would use in our environment, and they would start to melt. So when we started talking with Avid, we kind of presented this device and some of the challenges we've had, and said, well, is there something we can do that would be more cost effective, that we can do that would eliminate some of these other challenges? And we really kind of ran with it. And we've resulted with a product that's directly 3D printed. It's got some assembly, but it saved us a fair amount of cost. It's a much quicker process, and it's a more reliable part.
Yeah, no, that's a great background of the part. Drew, going into kind of that communication. So, this is a multi-material part. How did you navigate that? And I know you said there were some DFAM adjustments to this part to make it a better fit for the process. Can you go into those two things a little bit?
Yeah, absolutely. So, overall, the product had a certain length initially, the previous casted version, and the HP multi-jet platform has dimensions to its build volume as well. So, the most efficient way to stack these parts in a build would be to get the length of each section to be essentially the y-axis of the printer, or the smallest axis. That way we can get the density up, like David alluded to earlier, and fit as many parts in a build and get the cost down. So that was the first hurdle, was to just adjust the section length so that they were optimized. Next was finding suitable materials to have rigid on the outside and flexible in the middle. We chose PA12 for the ends, and Lubrizol's M95 TPU for the middle, which allows it to flex and hold like their previous casted version. So we needed to find a way to bond all three of those parts together with that metal rod in the middle to hold its shape. And what we found was using surface lattices on the part in the joint gave us more of a mechanical bond for the adhesives. So we found a adhesive that worked great for TPU to PA12, and then also added in our design some more mechanical surface area to grab onto the adhesive.
All right, thank you. So we're getting close to the end of time and want to make sure we have enough of a buffer for questions. Last question for Pete, and Drew, you can also give some feedback. So these are end-use parts. I know the head mount was dyed black. This part is smooth and dyed. For Pete, is your company happy with the surface finish and quality sending these out the door? And have your customers, noticed anything, or had any feedback saying about if they've noticed a difference with these parts versus how they've been traditionally made?
Yeah, I mean, with this extension device, we've been very happy with the surface finish. These use the chemical smoothing process, and it results in kind of a high sheen, very smooth process or finish, which is ideal for this device because it is a very messy environment and it needs to be very cleanable. The head-mounted display, we don't go for the smoothing process. We just dye it, and it ends up with a slightly rougher texture than injection molding, but it's been well received in our market. We manufacture these very rugged devices, and I think it kind of fits in that rugged look and feel. So I think it's gone over well.
All right, thank you. So moving on to that, I do want to make sure we have enough time for questions for our audience. Tom, I see there were a few that we can go over, and to all the attendees, this can be questions that are about the process towards me, towards Drew, towards Pete. So it is open discussion, and we can kind of go through some of those now.
All right. Sounds good. Do you want me to read these, David, or do you want to take them over? I know you have access to them as well. You're doing such a great job. I don't want to interrupt your flow.
I think I can. Oh, there. Okay, I do have a better. I can read them then.
Okay.
So I'll take. Sorry, I missed a few of these as I was going through. There was one asking, is it possible to print external threads on the cylinder? Yes, it is. So in our design guideline, we have the sizing of the threads that are printable. You can get some more information there. I would always recommend these are still thermoplastic parts. Depending on the requirements of the threads, a metal insert's always better. I know that's harder in external. But always keep in mind that if you break the thread, you have to reprint the part. So that is something to keep in mind as you're looking at the best way to design this. The material itself is also very machinable. So if it's a complicated thread design or a tighter one, then for printing, that is also a post-processing option. So the second question was, what is the chemical resistance for the medical equipment components? I think, Pete, was there any specific requirements on these parts with as far as the chemical resistance? I know you mentioned the cleaner for the rod or the ICE handle.
Yeah, for the ICE handle, we did need to make sure that it had a biocompatibility rating that was safe to be used in contact with animals. We're not beholden to the FDA, but we do want to make sure we're using safe materials, and it did meet those specifications.
All right, sounds good. And we do have some chemical resistance with our materials. I always tell people that these are, if we don't have information available, these are pretty common thermoplastics. So typically, if there is one that has well-researched in chemical resistivity, there's a good chance MJF will be as too. That's not 100%, so just kind of use that with caution. And also you can always ask to see if we do have any other information. So going back to the recyclability question, the process is recyclable. So the fusing agent will create the part, the detailing agent, there are a little bit of losses there, but typically we see about 80% of powder is recyclable. For, say, a new build, it's 80% recycled material, 20% fresh material. So it's a typical balance we see that might shift a bit just depending on the specific material requirements, or if there's a denser build, there might be a little more fresh material just to balance that. We had a question asking what colors are available. So right now in our production units, we have natural colors, kind of darker gray. Unfortunately, that is the only color available. But as you saw with these parts, there are vapor smoothing, which does darken the material a bit, as well as dyeing. So those are options that you can look at. You can always look at post-processing, like painting with priming, as you saw with that assembly manifold. This one is directed to Drew. If you can speak to the dyeing process in terms of labor, square footage requirements for the process, how much extra work? Is there some automation there with looking at these parts?
Yeah, so there's a couple ways you can dye parts. You could boil water in a pot with a vinyl dye or a standard RIT dye, or you can use some more automated equipment, which is what Avid has. So it's essentially a large washing machine. So think of square footage size and industrial washing machine. And I'd say labor, it's really low because we're just putting parts in there and shutting the door and letting it run its program. So that takes a few hours for a full build of parts, and parts come out rinsed and ready to sit on a drying rack.
All right, thank you. This one was for Pete, and I'll preface it with a little comment before letting you take it over. The question was, how is the biocompatibility ascertained? And we do have a handful of biocompatibility testing results for our materials. Across the board, there are, especially the ISO 10993 test results that kind of give you a guidance of material selection there. Pete, I'll let you kind of take over how you went through that process as well.
We really evaluated it based on the USP class FDA guidance for skin surface devices. So we relied on the test results that were based on the data sheets for the material.
Yeah, and I know the on the veterinary side, they're not as strict as far as some of the class devices as well. Was there any additional things you were considering with that in mind?
No, I mean, we did do, because in our previous device, we had some challenges with some of the chemical cleaners that some of the practitioners would use on devices. So we did do some kind of accelerated life testing for that, but it wasn't really meant for biocompatibility. It was more just to test the material against, fatigue and wear from chemical.
All right, sounds good. And this will probably be the last question, just to give enough time for everyone. Someone asked, in classic machining, you can't put metal back on. With additive manufacturing, can you take a finished part and add material onto it? So with multi-jet fusion or thermoplastics, I mean, you can, depending on how that looks, it may not come out great. On metal, there's a specific process called directed energy deposition where you can actually repair parts as long as it's the same type of material. But with that, these do have a bit of flexibility within almost repairing it. But as far as like printing material back on, that's not possible with this process. All right, so we'll kind of close out. We did get a comment saying thank you so much for making Pete's and Drew's knowledge available to everyone. So again, thank you to our speakers. I always like to get real customers in here versus me speaking the entire time, just to kind of show, they have a very hands-on experience, which is very valuable, I think, for a lot of people kind of dipping their toe into this. I did offer our contact information if you have any questions. And Drew and Pete, what's the best way for people to get a hold of you or learn more, kind of keep an eye on the companies or your company?
Reaching out by email, certainly. I'm more than happy to answer any questions and talk through any projects you have or give advice. So email is great for me.
Yeah, same for me. I'm happy to reply to any emails with any knowledge that I can share.
All right. Well, thank you to the both of you. I really appreciate your time. So for attendees, just to know what's next, we will have a follow-up email. There are some URLs. One was not user-friendly for the healthcare aspect of our website, so we'll have some more information on that as a follow-up. Tom mentioned that we did have a Device Talk Tuesday. The topic was how 3D printing is getting products to market faster. So that'll be a bit more information outside of what we covered today. The URL is here. You can also just look up Device Talks Tuesdays and look for that title in the agenda. And Tom, I will let you take it over from here to talk about the Device Talks Boston. It is an event that HP will have a booth on, so if you are close by or happen to be going, you can actually see some of these parts in person, talk with some of my other colleagues there, and there are a few presentations HP is also providing as well. Great
job. I'd love to have you back hosting another webinar at some point, David, even if it's not yours. So you do a good job with the questions. It would be great to see you in Boston. We will be at the Boston Convention and Exhibition Center May 10th and 11th. There's, as David said, there's 3 meetings. So Device Talks Boston, which is the one I'm organizing. The robotics are the largest event, and the Healthcare Robotics Engineering Forum. You can go to devicetalks.com. You can go to roboticsummit.com. You can register for any of them, and you can attend all of them. And we'll have a huge exhibition floor, and you'll be able to visit HP down there. And lots going on. So I hope you'll join us on May 10th and 11th at the Boston Convention and Exhibition Center. So, and do you know the booth number, by the way, David? You could probably find out real quick. I do not offhand. That is a very good question, though. Should have checked that. Let me see if I can do that while also doing other stuff as well. But we'll advance the slide. And once again, this is available on demand at metaldesignandoutsourcing.com. And let us see if I can find you on our map. There's just too many. So you guys go to roboticssummit.com. There's a sponsors page. And there's a lot of great sponsors, including HP, and you can find out where they'll be. But it's not one of these floors that goes on for forever, but it's got all the right people on it, so you'll be able to find them. So make sure you do visit. And that's it. That's a wrap. Thank you for joining us on this episode. Thank you, HP, for sponsoring. Anything else, David, from your side?
No, thank you for having us, and a special thank you to Drew and Pete. I love talking with you guys about applications, and this really shed some great insight for what you've done so far.
Absolutely. You guys did a great job. It's very entertaining. And if folks, you still have questions, once again, you can check it out on demand, and you can ask questions there, and we'll make sure it gets over to the speakers. So that's it. Thanks for joining us. We'll see you again in the future at an MDO webinar.